All right, guys, so thanks for coming. We're going to kind of review for the midterm mostly by doing problems. I'm hoping that the problems will maybe prompt questions that you might have, and so you can certainly feel free to fire questions out at me. This is a pretty open-ended thing. I've got all the time in the world for it, so no particular rush. I'm going to be going through the review session number 1 problems handout, which has, 17 problems on it. So there's actually quite a bit here. We have done a little bit of this in the past, so it won't, some of these things we might be able to go a little bit more quickly through, but it will definitely take us a little bit of time. And I also, I guess the last time I taught this class, I actually gave quizzes. I haven't been doing that this time, so I printed out some of these quizzes, and I thought, oh, these are some decently good questions. So I think maybe I'll grab a question or two off of this quiz page as well. So we'll kind of just jump around a little bit. On the exam, make sure that you do not view it as an all or nothing proposition with respect to your solutions. Like, don't think of it as, oh, I either know it or I don't know it. Because you probably do know a lot more than you give yourself credit for that I would actually give you points for. For example, let's suppose that I ask you to prove some isomorphism like that, right? And if you have maybe no idea how to do the details of it, but you recognize that this is well set up for the first isomorphism theorem, and you say that, I should use the first isomorphism theorem, and the more you can say, the better, right? Define a function from G onto H, whose kernel is N, right? If you say all of that, but then you don't do anything else, right, you're already going to get some partial credit for that. So please write down your thought process. The more you write down, even if it's just a partial progress, maybe you know it's not fully comprehensive, but I can give you points for that. I basically try to give you points for all of your knowledge of everything. So a lot of what it takes to do well on my exams is the communication side of it, and that means getting things onto paper. So make sure that you tell me what you're thinking about as you go through it. So just stuff like that. Don't let one problem throw you off. As I mentioned, I probably will not make any particular problems worth huge numbers of points. Maybe 10 points for one problem would be about the most you would see. And so if you're stuck on something, instead of continuing to sort of beat on that one problem over and over again, let it go and try to work on some other things first so that then you can come back to it. Get as many points figured out, as many things solved as you can, as quickly in the hour and 15 minutes as you possibly can, okay, so that you can maximize your credit. Also, please try to be there early, and that way if everybody's in their seats ready to go, I can have my substitute just get things started right away. Give yourself the maximum amount of time. I'm going to give you about an extra 5 or 10 minutes at the end, but not much more than that. Okay, so just some test taking stuff, just to kind of be wise about that. Yeah, Matt?
You mentioned that you were probably going to have you would drop the lowest question on
something like that, or I used to do that, and then what I ended up doing after a while, I would let students cross off a question, and then I would find out later that they didn't cross off the one that was best for them to cross off. So I started changing the way I do things to where I sort of say, yeah, do the whole exam, and then I will go back later and figure out sort of what would be the best for you to drop. It may be that there are certain things that you cannot drop, but I might let you make some choices, or I might say, oh, I'm really only going to keep your 4 best of these 5 parts or whatever. That way you could choose to skip a part if you wanted, or you could just do the whole thing and then let me figure out which one would be to your advantage for me to drop. I could just do it like that too. So something like that. I haven't totally figured out the exam yet, but that's kind of what I'm thinking. Okay, so yeah, without further ado, why don't we go ahead and get started. I've already talked about what the exam is going to cover. It's obviously completely a group theory exam. for this one. So I'm going to start in the review session packet. I'm not necessarily going to go in order, and I won't necessarily do all of these, but I'll start with number one. Number one asks the following question: is the cyclic subgroup of S4 generated by the cycle 1, 2, 3, 4, is that a normal subgroup of S4? Okay. So let me propose an answer to you and let me see what you think. This is obviously cyclic. Anything cyclic is always abelian, and in an abelian setting, everything is normal. So therefore the answer is yes. Do you like that proof? You shouldn't like that proof. I heard a lot of people saying things like that I didn't hear it, I saw it in their homework solutions a few times. It is true that this is an abelian group, but what that means is that every subgroup of it would be normal in it, right? That's not what this question is asking. This question is asking, is this guy normal in this much bigger group over here that's not abelian, right? So S4 is not abelian, so therefore a subgroup of it may or may not be normal, right? What's the index going to be here? What do you think the index is going to be? Take the size of S4 is 24, right? We're going to divide that by the size of the cyclic group generated by 1, 2, 3, 4. How big is the cyclic subgroup generated by the cycle 1, 2, 3, 4? 4, right? Because remember that the size of a cyclic group is just the order of that element, which is just the length of that cycle. So this is 24 over 4, which is 6, so it is not of index 2. Okay, so that doesn't seem to be working. Tell you what, let's actually write out what this cyclic subgroup is. So if we write it out, 1, 2, 3, 4, it's just all powers of this element, right? So starting with E, we would then have 1, 2, 3, 4. Can somebody tell me what is 1, 2, 3, 4 squared?
2, 3, 4, 1.
No.
Sorry. 1, 3, 2, 4.
1, 3, and 2, 4, right? So you move 2 spaces to the right, 1 goes to 3, right? But then 3 goes back to 1. Sorry, 3 goes over to 4 and then back to 1, right? So 1 and 3 permute with one another, and then similarly 2 and 4 alternate with one another. Okay? So that's that element. And then what would be the cube of the element 1, 2, 3, 4?
1, 4, 3, 2.
Exactly, 1, 4, 3, 2, right? So that's just starting with 1 and going 3 steps forward. So 1 goes to 4. If I go 3 steps forward from 4, I'll end up at 3. If I go 3 steps forward from there, I'll end up at 2, and so on. Or you can just think of it as the inverse of this element. Actually, this is just isomorphic to Z4, right? And this is like 0, 1, 2, and 3. Okay, so the inverse of 1 is 3. The inverse of this guy is itself, because it has order 2, and so on. Okay, is everybody with me? Okay, so this is just calculating a pretty simple calculation in S4. I wonder if that'll help me decide if this thing is normal or not inside of S4. So remind me again, what does it mean for a subgroup to be normal?
Closure under conjugation.
It's closed under conjugation, or in other words, right cosets and left cosets are equal. I like to focus when I have elements in front of me, I like to use the conjugation idea, closure under conjugation. So is this going to be closed under conjugation? If I take one of these elements and I conjugate by something, will I get another element that's still listed here? This is where you really have to absorb and appreciate the videos that I've made, because I made a video about conjugation in SN. And in particular, what I said is that if I have an element, I'm just going to recall this little fact from my video. If I have an element tau, let's try that. If I have an element tau, let's just say it's the cycle from 1 to k. And if I conjugate that by sigma, which is some other permutation in the symmetric group of whatever, what I get is another cycle of the same type that is made up of sigma of each of these things. Sigma of 1, sigma of 2, up to sigma of k. Do you guys remember this? So a k cycle gets conjugated to a k cycle. Now, the sigma that you're conjugating by can be any permutation whatsoever in the whole S4, which means that you can rig this. You can rig this list to be any 4 numbers that you like in whatever positions you want them to be, because you could say, well, I want sigma of 1 to equal, I don't know, 1. And I want sigma of 2 to equal 3. And I want sigma of 3 to equal 2. And I want sigma of 4 to equal 4. I could do that, right? I could literally make any other 4 cycle out of this original 4 cycle. Let's assume that k is 4 for a minute. Right? What it means is that in order for this set to be closed under conjugation, the minute I see 1 4 cycle in the set, I will have to have all of them, every 4 cycle. So I could conjugate this, 1, 2, 3, 4, by a suitably chosen sigma and make a 4 cycle that's not in this list. Notice I only have 2 4 cycles here. There's a whole lot of other 4 cycles in S4, right? So the answer is no. This is not, it is not closed under conjugation, okay? So if you need to watch my videos again or ask me some questions about how conjugation in SN works, this is a very important thing, okay? So it's not closed under conjugation. And if we wanted to give a specific example, which is usually what you would be expected to do, you might take, well, we can just do exactly what we just did a moment ago. We can take 1, 2, 3, 4. We can choose our sigma to be, let's see, what does this sigma do that I chose here? Sigma fixes 1. It sends 2 to 3 and 3 to 2. Okay, well, that would just be the cycle 2, 3. And of course, the inverse of that is just itself. Okay, and if you now multiply this out, we already know what we're going to get, right? You can just check it. 1 goes to 2, then 2 goes to 3, so 1 goes to 3. 3 goes to 2, 2 goes to 3, 3 back to 2 again, right? And 2 goes to 3, 3 goes to 4, so 2 goes to 4, 4 goes to 1, and we're done. That's the end of the cycle. Okay, exactly what we predicted. Okay, and then the point being that this is not in this cyclic subgroup generated by 1, 2, 3, 4. Okay, so it's going to be, for giving examples of things, the symmetric group is really handy, especially if you know how to do these cycle calculations, which I want everybody to be not just able to fumble through them, but to literally be like, boom, 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 I know exactly what I'm doing. You want to be really slick and fast with things like cycle permutations, multiplications. Okay, does this make sense? So this is not a normal subgroup. I actually asked a question as well here. I said list, so this is also a part of problem number 1. It says list the right cosets of this subgroup. Maybe I can just call this, I'll just call this K for now. List the right cosets of it. So how many right cosets will there be? The number of cosets, right, is the index of the subgroup inside the whole group. So there should be 6 of them. This is actually going to be a little bit of a pain, right? So the first coset is K itself. So K itself would just be the one we already wrote down. E, 1, 2, 3, 4, the 1, 3, 2, 4 transposition pair, and then 1, 4, 3, 2. Okay, so there is a coset. That's just, of course, that's the same thing as KE, right? You're just taking, the identity element there and multiplying it by these four things, okay? So then to write another coset, what do I need to do?
Pick an element in S4.
Pick an element in S4 that's not been listed so far, such as?
1, 3, 2, 4.
1, 3, 2, 4. Okay, I'll take that one. So all I'm going to do is take each of those four things and multiply by 1, 3, 2, 4. So this is actually a lot of practice with cycle multiplications. Maybe I'll just do this one, and then after that I'll stop writing them all out. But you're going to take 1, 2, 3, 4 times 1, 3, 2, 4, and then you're going to take the cycle 1, 3, comma 2, 4 times 1, 3, 2, 4, and then you're going to take 1, 4, 3, 2 times 1, 3, 2, 4. So you literally are just going to calculate this thing, right? So I'm just putting the 1, 3, 2, 4 on the right of everything that's in this list. So now you just have to calculate this, 1, 3, 2, 4. And then this one, of course, starting at 1, you go to 3, but then 3 goes to 4, so 1 goes to 4. 4 goes to 1, which then goes to 2. 2 goes to 4, which goes back to 1. So it's going to look like that. Okay. This one, if I start with 1, it goes to 3, but then 3 goes back to 1, so I don't have to write that down. 2 goes to 4, which goes back to 2, all right? So 1 and 2 are both fixed. And I already know, therefore, that 3 has to go to 4 because it can't be the identity element. That's the only other thing it could be. How about this one? We've got 1 going to 3 and then 3 going to 2. So 1 goes to 2. 2 goes to 4. 4 goes to 3. So 2 goes to 3. And 3 goes to 2, which goes back to 1. So we would have that. That would be another right coset. Okay? Everybody knows how to do that, like lickety splits. Like, if not, you've got, 5-6 days to just hammer this home and practice it. Find a partner and do a speed test. See who can go the fastest. Getting those done quickly is a good idea. So I've written down 2 of the right cosets. There will be several more. It might not be so interesting to write out the other ones. It would be interesting perhaps to calculate a left coset that's different from this. For example, this right coset is not going to be the same as the left coset. So you could show that, and that would be another way of showing that your subgroup is not normal. I prefer closure under conjugation as a good test, but you could compare right cosets with left cosets. That would be allowed. Okay. Does it make sense to talk about S4 modded out by this subgroup? Does that make any sense?
No.
Not if your subgroup is not normal. Right, so this is not a normal subgroup of S4, so I wouldn't even be talking about a group here. Like if I asked you, to what group is this G mod, the cyclic subgroup isomorphic, right, you would be looking at me funny, like, what are you asking, right? There is no group there. Right? In order to have a quotient group, your subgroup has to be normal, so we really shouldn't even be writing this down. Okay. Okay, are there any questions so far on sort of this first one? I won't go, in my solutions I actually wrote out all 6 of the right cosets and left cosets, so if anybody wants to just practice the whole thing out, you can, but I think this is maybe gives you enough of the idea. Clear enough? Okay, let's go on to another problem. For now, I'm just going to go in order until I feel like there's some things we need to touch on. Let's do number 2, which is just find the order of the element. And I have 2 parts to this question. So the first part is going to be the element consisting of R1. This is a 90-degree rotation in the D4 group. And then the cycle 1, 2, 3, 4, 5, and then the class of 6, when viewed as an element of D4 cross S5 cross Z15. Okay, I didn't want to make this too easy. I'll make us struggle with this one a minute here. By the way, guys, the purpose of the review session is not for you to walk out of here in 2 hours thinking, oh, I'm ready for the test, I don't have to think about anything else. Right? I'm trying to open your eyes to some of the things that maybe you want to put a little mental star next to, that, ooh, I need to review that. Right? So I'm trying to pick, it's going to be pretty comprehensive. I'm trying to pick as many things to talk about, different topics, to just kind of get you going, and then that'll hopefully guide you in the rest of your studying when you get ready to practice the sample test and some of the other questions in the review packet. Okay, so this is a direct product of 3 groups, and I've made an element that is a triple where I've grabbed one thing from each group. So this is like a chance for me to really test like multiple things at once. Does anybody have a suggestion how, not what the final answer is, but how to approach it?
Find the order.
So, Justin, I'll let you jump in.
Just find the orders individually and then the LCM.
Okay, great. So we would just find the orders of each slot individually. So like, for example, the order of, I'm just going to write the word order, I hope you don't mind. I don't like those absolute value bars very well, actually. So the order of R1 in D4 would be what?
4.
It's 4. That's just a 90-degree rotation. Okay, and then what would be the order of the cycle 1, 2, 3, followed by 4, 5 in S5?
6.
It's 6. It's always the least common multiple of the cycle lengths, assuming that this has been simplified and has no common numbers in the cycles. This has to be a disjoint cycle representation. In other words, if I gave you this, and I said, what's the order of that element? You would not say it's, the LCM of 3 with 3, because it hasn't been simplified yet. I would first need to like multiply this out. Say, okay, so 1 goes to 2, 2 goes to 3, which goes back to 1, right? And then 3 goes to 4, and 4 goes to 3. And then once I've simplified it, now I can say, well, what's the LCM of these cycle lengths? So this is actually an element of order 2. So make sure you simplify these cycles first. In this case, it's already simplified. So we just take the LCM of 3 and 2. Okay, and then the next one is the order of the the order of the congruence class of 6 in Z15. Does anybody want to help me with that?
5.
It's 5. So how do you get that?
15 divided by GCD of 6 and 15.
There you go. You take 15 and you divide by the GCD of 6 and 15, which is 3. So this comes out to 5. Okay, so we have first slot has order 4, the second slot has order 6, the third slot has order 5. So every 4 powers of this element brings the first slot back to E. Every 6 powers of this element brings the second slot back to E. And every 5th power, in this case multiple, of the third slot brings this third entry back to E. So when do it's like gears that are spinning around, right? Every 4 times you apply the element, this goes back to the identity. 6 times here, 5 times here. So the overall order is just going to happen exactly when all 3 of them, when you have a number that is a multiple of all 3 of them. And the smallest such multiple would be, what's the answer going to be?
60.
Yeah, I think it's 60. Looks right to me. Yeah, great. Okay, so that's that one. Make sense how to do something like that? Okay, let's go ahead and do a part B on this. Let's take another one. Part B, let's find the order of this element. So I'm going to take the cycle 1, 2, 3, 4, 5, 6, and then the element, or the cycle 7, 8, 9, 10, and I'm going to quantity cube that in S10. Okay. So I'm going to figure out the order of the cube of this thing in S10. Okay. Anybody have any thoughts here?
Was it the same notion as the GCD? Wasn't it like n over GCD k and n?
Yeah, what's the n in this case?
The order of that element by itself.
Yeah, we need to figure out the order of the element inside the parentheses first, right? Before we worry about the cubed part. So can somebody tell me what will be the order of just the part in the brackets?
12.
So how do you get 12 there, Justin?
6 and 4, and then LCM.
Exactly. The LCM of 6 and 4, which is 12. So this element here inside the brackets has order 12. So the order of the cube of the element, what do you think that's going to end up being? The overall answer for the whole thing?
4.
Yeah, so the order of that would be, well, you take the order of the base element and divide by the GCD of that order together with the power, which was 3. So 12 over 3, which gives you an answer of 4. If you think about it, if I call this little element in here sigma, right? What we're saying is that sigma to the 12th is the first power of sigma that gets me back to E. So then what's the order of sigma cubed? Like how many times do I have to multiply sigma cubed by itself to get back to E? Well, I only have to do it 4 times because you're getting 3 powers of sigma at a crack when you do that. Okay, let's do another one. Stop me with questions, guys, if there's anything
Yeah, I have a
unclear.
question about the order of 6. So
This one.
Yeah.
Yeah.
So when you square 6.
Oh, but we're not really squaring 6. We're adding 6 to itself. Because this is a group under addition. So you have to use the, I just erased the group, but the operation in Z15 is addition. So when I ask you about what is the order of this class, we're asking how many times do I have to add 6 to itself to get back to a multiple of 15? And the answer is 5 times. Yeah. Okay, great. Yeah, the group operation can be a little bit interesting. So I'm starting off here, as you can tell, with just some computational examples. The midterm is going to have some computations in it. I mean, it's also going to have some theoretical results too. So I'm going to try and get to a bunch of all of that stuff. Okay, so here's number 3. Suppose, this is a hugely cool observation. Suppose that I have a function f that goes from z to S8. And let's suppose that this is a group homomorphism. Okay. Such that, by the way, would it be possible for this to be an isomorphism? No. These things are the wrong size. This one's abelian and this one's not. Or this one's cyclic and this one's not. This one has elements of infinite order. This one has no elements of infinite order. You know, you go on and on, right? There's a whole bunch of different things you can quote there. So definitely, it's not going to be an isomorphism, but you could potentially have a homomorphism such that f of 1 is equal to the cycle 1, 6, 2, 5, 3 times the cycle 4, 8, 7. Okay, and what I would like to do, this is another computational problem, I would like to compute f of 20. One of the amazing things about working with homomorphisms on cyclic groups, and this function is cyclic, is that as soon as I tell you where f sends a generator for that group, I can actually figure out what f does to everything in that group. I just picked 20 rather randomly here. I could pick any number that I wanted, right? So this is one of the beautiful things, especially when you have a group that's generated by a small number of elements, is that the structure of that group can be pretty quickly gleaned just from what's going on with the generators. Yeah. Anybody have an idea how I'm going to do this?
Just figure out the order of F1 first.
Figure out the order of 20?
F1.
Oh, f of 1. Figure out the order of this guy.
Mhm.
Okay, we can certainly do that. The order of f of 1, and this will be inside of S8, right? What is the order of this cycle? It's 15, right? Okay, great. So this is 15. All right. Now what do you want me to do?
So I really only have to calculate f5.
Right. So you're using the homomorphism property, right? You know, which is I think what you were looking at, right? So in other words, see f of 20. This is just f of 1 plus 1 plus 1 plus, you know, on and on and on. Notice that I'm using addition in the group of integers here. But then the homomorphism property allows me to write that as f of 1, well, times, because I'm using multiplication in S8. So it's f of 1 times f of 1 times f of 1 as individual results. And so this is f of 1 20 times as a power now. And so what we observe, I think what Robert's getting at is that, well, if I take 15 powers of f of 1, I get e. So I can cross off 15 of these guys and just write this as f of 1 to the 5th. Okay. So in other words, I would like to know what is 16253 times 487. I would like to know what that is to the 5th power. Oh, this is easy. This is actually very easy. Because these cycles are disjoint, they commute. So disjoint cycles commute. Does that make sense? That should be the case?
Oh
Yeah, because they don't have anything to do with each other, right? So here, this cycle just permutes the numbers 1, 2, 3, 5, and 6, whereas this cycle permutes the numbers 4, 7, and 8, and those things happen independently of each other. So if I do this one first and then do this one, it's the same result as if I did this one first and then this one. My point being that you can choose to calculate this by putting all of the powers of the first element together and all of the powers of the second element together and calculating them separately. Okay. And normally you can't do that unless you have commutativity of the elements. If a group was abelian, for example, you could always do that, right? In this case, we're not in an abelian group. S8 is not an abelian group, but I am working with two specific cycles that do commute with each other, so I can still use that same idea. And what is going to be the 5th power of 16253?
So
It's just
For 16253.
for 16253 to the 5th power, I'm gonna get the identity element, right? This one's gonna be e because the order of that element is 5. How about 487 to the 5th?
47
4,
squared.
7, maybe.
47.
Yes, that's right. So it's basically 487 squared because 3 powers of 487 goes away, and that leaves me with 2 more powers. And when I square this element, I just end up getting 478 exactly. So that would be the answer to that. Yep, that's exactly what I got. Okay.
Was there another way to do that one,
To do this problem,
or was this the way?
this was the way.
Oh, okay.
Yeah, this is what I had in mind. I mean, I could have made the power much bigger. I only made it the 20th power. I could have made it a little harder to calculate it, but that's the idea.
This will be like a good one for like 2020.
2020?
If you make f of
Oh.
2020 and then divide, we would have to divide 2020 by 15 and see like.
That's right. So if I asked you, so what if I asked you what is f of 2020? I mean, you wouldn't have to divide by 15 and take the remainder. You could just say, all right, I'm just going to calculate 16253 to the 2020th power and 487 to the 2020th power, and then you can say, so instead of dividing by 15, you can just say, well, this is a multiple of 5, so that's still e, right? And then this one, I would want to know modulo 3, what this comes out to be, and it would be 1, I believe. So, you can just check.
Modulo 3.
Modulo 3, just because it's a 3 cycle. And so this one would come out to 487, actually, in this case. This is, of course, a different power than what we had before, so we would be expecting a different answer. Yeah, that's true. But yeah, so I could definitely make the numbers bigger, and it would be conceptually the same kind of thing. Okay, let me see where I want to go with this. I'm gonna jump around a little bit. I'm gonna do something now that's a little more of a proof, I think. So let me go on to problem number 8 on this review list. We may come back to some of the other ones. I just want to do this one first. Okay, so here's what it says. Let G1 and G2 be groups. Prove that the center of G1 cross G2 is equal to the center of G1 crossed with the center of G2. So we've just recently learned about the concept of the center of a group. Let's just see if we can write something like this down. So this is kind of nice. You can, if you want to know the center of a direct product of groups, well, you just take the individual centers and cross those together, and that's going to be the answer. Any thoughts on, maybe not the whole thing, but just how would you maybe think about starting something like that?
Would you do the contained in one thing is contained in the other, and then vice versa?
Show containment both ways. Yeah, show the left side as a subset. So this is a set, right? And this is a set. So when you're trying to show two sets are equal, a great way to do that is to just show that the first side is a subset of the second side and vice versa. If you're taking the test and maybe you're a little flustered, like, oh, I don't know what to do, I don't know what to do, probably the first thing I would do is just write down the definition of the center, just to have that in front of you. In fact, I'm going to do that right here. I'm just going to recall what the center is. So the center, Z of G, this is the set of elements, I'll call them A, in the group, such that, and I'll write this multiplicatively, so AX equals XA for all X in the group. And that for all X in the group is absolutely critical. Okay, so you're talking about the elements that commute with everybody, right? That's very important. Okay, so let's try and prove, let's take Tuan's idea here, let's prove subsets both ways. So let me go maybe from the left side towards the right side. So I'm going to pick something in the center of G1 cross G2. Now let's make sure that we write a notation for that that fits the setting. We're talking about a cross product of groups, so the elements that I'm going to write down should be pairs of points. Okay, and so I would want to see you write that down as something like this. A comma B, let's call that an element of the center of G1 cross G2. So we grab something from the left side. What I have to do is show that that element lives also on the right side, which means I basically need to show what? Like, what do we need to show? I'm going to write this down. We need to show, what do we need to show here, guys?
A is in the center of G1, and B center of G2.
A is in the center of G1, and B is in the center of G2. Very good. That's exactly what we need to show. And I'm going to forget about this right now, and I'm going to focus on what I'm trying to show. Let's just focus on this one. I want to show that A is in the center of G1. In other words, I want to show that A commutes with everybody in G1. Right? Okay, so now how do I prove that part there? So to show that A is an element of the center of G1, what would I need to do?
Pick an arbitrary
Find an
element.
arbitrary X.
Take an arbitrary element. I'm just going to really make this clear to myself, I'm going to call it little g1. You could call it X or any other letter you'd like. But I'm just going to grab this element, and this is, as you mentioned, this is arbitrary. So we're going to take an arbitrary element, little g1, in capital G1, and my goal is to show that AG1 equals G1A. Right? That's what we need to do. Show that AG1 equals G1A. That's to prove this box, that's all I have left to do. Now my assumption has to come into this somewhere at some time. The assumption is that A comma B is an element of the center of G1 cross G2. Can I use that? So I know that the pair AB,
We know that it commutes with the element, so we know it commutes with the element GE, for instance.
it commutes with everything, right? Every pair that you could possibly write down.
G1E.
Right, so we know, exactly, so we know already that if I take AB, it's gonna commute with anything I wanna put here, and obviously I would be inclined to put G1 there. Now I don't have an element from G2 in my hands right now, but as Matt said, there's no reason why we would need to get nervous about that. We could just put the identity element for G2 there. By the way, if you don't write the G2 subscript, it's okay because I'll understand that that's coming from the second group. That's just by notation. So we already know that this is the same thing as G1E multiplied by AB. And we can now just multiply out the products of these pairs. So on the left side, I have AG1 comma B times E. And on the other side of the equation, I have G1A comma EB. And if two pairs are equal, then their slots are equal. You can sort of see this is what you're trying to drive at anyway, right? Trying to get AG1 equals G1A. Mm-hmm.
So now that we know the trick, can we replace the E with a G2 and then knock the B out?
I wouldn't do that. That would be kind of mixing the two parts of the proof together, and I think that's a recipe for confusion. Yeah, let's just prove this one. Now, if you want to say something like similarly for the second one, I will let you do that. That's okay. But I think to sort of do this whole thing in one breath would be, I mean, you could say, I want to show that B is in the center of G2, so I'm also going to grab a G2 from G2, and then you could build one single element that proves everything. You could do that, but I think for you guys, it's probably fine. But if I was thinking for like everybody at Cal State Fullerton, probably better to do it like one little step at a time. Yeah.
I was gonna say for a proof like this as well though, because there's a lot of things you have to prove for both the subsets. Could we prove it a different way by doing a contradiction proof? Then we only have to prove one, so we would assume that they're not equal.
Assume that this is not a subset of this, for example?
For instance, yeah. Or sorry, we would assume that, I guess if you assume they're not equal, you still have to do both directions. So,
I mean, proof by contradiction is certainly valid.
Yeah.
I think it will not be a good way to go here.
No.
I think it will end up being just as much work and a little bit kind of confusing in the logic of it. Yeah. Yeah, this isn't so bad. You know, I've been writing everything out. Like you could probably get away with a little bit shorter write-up if you really wanted to. So this proves, this calculation, this is just looking at the first slots, this proves that in fact A is indeed in the center of G1. And then we're just going to say similarly, B is in the center of the second group G2. I think that's perfectly fine, okay? And therefore, thus, A comma B is in the right-hand side of what we're proving over there, the center of G1 crossed with the center of G2. Great. Okay, so that's half of the proof. So have to prove the other way, don't we? I guess I can at least start the backwards direction on this side. And what I'm going to do for this is I'm just going to start over. Let me take another pair, A comma B. This time this is an element of the center of G1 crossed with the center of G2. This just means that A is in the center of G1 and B is in the center of G2. So we already know all of that. Okay. guys like to try this on your own first? I don't want to steal all your fun here. I have to show that AB is in the center of G1 cross G2 from that information. So I picked an element. The first slot is in the center of G1. The second slot is in the center of G2. What do you think I need to do next? Think about what I'm trying to prove. I want to prove that this element is in the center of G1 cross G2. Means I have to prove that this element commutes with everybody in G1 cross G2. So what do I need to do up here to get this started?
An arbitrary element of G1, G2.
There you go. We need an arbitrary element of this direct product, right? So let's just do that here. Let's let G1 comma G2, which is an element of capital G1 cross G2, let's let this be arbitrary. There we go. Okay? And so I'm just going to try to show that AB commutes with that. It really just means, well, do you guys want to tell me? I hate to steal your
Just take the product of them.
You multiply them.
Want me to multiply them? Okay, so then I could take AB and multiply it by G1, G2. This is, after all, what we're interested in, right? This is going to be, by just the multiplication, AG1, comma, BG2, right?
You know
Now what?
You know that A and B commute.
With their respective elements, right? So yeah, I can switch the order of each slot sort of separately here. So for this part of the proof, we do get to do both of these pieces together. And then I can just pull it back apart again, right? So I can just put the G1, G2 in front, and then the AB in the back. The key step is really this one right here, okay? So maybe this step could be explained. A is in the center of G1, and B is in the center of G2. We can just add that to help clarify things. Okay, and thus, A comma B is in the center of the product G1 cross G2. Yeah, so something like that would probably work pretty well. Okay.
For this proof,
Yeah.
could you have done like a ladder of like equivalences starting from like letting an element be in the center of G1 cross G2?
So sort of say AB is in the center of G1
If
cross
and only
G2 if and only if blah 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 blah. So your blah 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 would have to be AB times G1 G2 equals G1 G2 times AB
And then
for all G1 and G2 in the group.
you can multiply them how you have them here.
Mm-hmm. Yeah. You could like. You could probably make that work. I think that, again, for most people, this is going to be a more clear way to do it, but you could make that work. Yeah. Okay. Let's go on to another one. Oh, yeah, I wanted to do, actually, let me, I've already done that one before. I've actually really done a lot of this stuff. Okay, let's do number 16. Let me come over here. I'll go back to some of these other ones too. I want to kind of hit some of these highlights first. So I'm going out of order, as promised. Okay, so number 16 says the following: show that a non-abelian group of size 8 must contain an element of order 4. Now, I don't want you to just simply say, oh, the only non-abelian groups of order 8 are Q8 and D4. And we know that both of those groups have elements of order 4, right? I don't want that. I don't want us to assume that we know sort of categorically what all the groups of size 8 are. Let's just say we don't know for sure what the groups are, but we have some mysterious group here, right? So, you know, some mysterious group G with size 8. And I want to show that it has to have an element of size 4 in it, or of order 4 in it.
Just to be clear, going into the exam, it's okay if I don't know like all these groups of certain sizes and them categorically, or just for this problem?
So maybe that's a good question. So what groups do I expect you to know about? I expect you to know that for primes, up to isomorphism, the only groups of prime size are ZP. Do you remember how to prove that?
Sorry, can you repeat the question?
Question is, okay, actually, so we're gonna take a diversion. We'll blame Tuan.
Sorry.
That's okay, no, this is a good question. Because this is something, remember what I said yesterday? Somebody asked me about proofs or whatever for the exam, and I said, I won't ask you something on the test that would depend on you having studied and memorized something very specific, but I would put a proof on the test that I think is something you should be able to recreate with your knowledge in a relatively easy way. And this is one of these. Let me just call this actually I think it's actually a theorem in the book. I don't remember what number it is, unfortunately. I'm not very good about numbers of theorems because there's so many of them. But the theorem is that if the order of G is P, where P is prime, then G is isomorphic to ZP. This is an example of something that I would expect you to be able to prove, even if you didn't study it 5 minutes before the exam and it happened to be the thing that you suddenly remembered from your studying. I would expect you to be able to produce this one. Any group of prime size is cyclic. Does anybody know how this works? Go ahead.
Wait, did you say it's cyclic?
Yeah, ZP. Any group of prime size is a cyclic group, and we want to prove that. Go ahead,
The
you can-
subsets have to divide P, right?
Okay, so what theorem is that?
Lagrange.
Yeah, so the most important theorem in finite group theory, I would think there's a good chance that'll be on the exam. This is Lagrange's theorem. It says that the size of any subgroup always divides the size of the group. So what you can do here is you can just simply grab an element out of your group G, right? With that element, I'll call it A. Assume it's not an identity element, okay? So your group obviously has size at least 2. In case anybody's wondering, 1 is not a prime. So a group has at least 2 elements in it, so grab one of your non-identity elements and then you just consider the cyclic subgroup generated by that element, okay? And the point is that the size of that has to divide the size of the group G, which is P. This is by Lagrange's theorem. So this is probably already in your notes because we would have proved this in class. But the only divisors of P are 1 and P, right? So since A does not equal E, then the size of this cyclic subgroup has to actually be equal to the whole P, and that just means that your element generates the whole group G, okay? Thus, G is equal to the cyclic group generated by A, and so G is isomorphic to ZP.
So
Okay.
we can't reference homework let's do tomorrow?
For this problem, I wouldn't want you to do that if I actually asked this question, because yeah, you could just say, all right, it's by the fundamental theorem of finite abelian groups. Actually, I didn't assume that the group was abelian to begin with, so technically you wouldn't be able to reference that theorem if you didn't know it was abelian first, and in the meantime you're going to prove actually that it's cyclic. So, okay, so I still didn't fully answer your question, Tuan. This is just, so I expect everybody to know what the groups are that are of prime size. Okay, I also think everybody should know what other numbers are there that are fairly small. These are, well, let's just start with that. These are some other fairly small numbers that are not, actually, these are some non-primes up through 12. Maybe I should have made a full classification. Anyway, groups of size 4, you are certainly allowed to use the fact that there are only 2 groups of size 4 and they are both abelian. So Z4 and Z2 cross Z2. What about groups of size 6?
S3.
Okay, we have S3 and Z6, right? And those are the only ones of size 6. Okay, for size 8, we of course have several abelian groups that we learned about yesterday. So Z8, and then we have Z2 cross Z4, and then we have Z2 cross Z2 cross Z2. And then what are the other groups that you know of size 8?
D4 and Q8.
D4 and Q8, right? Okay, and that's actually the full list. Okay, those are the only groups of size 8. What about groups of size 9?
Z3 cross Z3, Z9.
Okay, we have Z9 and we have Z3 cross Z3. Do we have anything else? Oh, I'm so glad that this came up because it gives me a chance to remind you about something. We actually should be able to fully classify all groups of size 9, not just the abelian ones.
We have a theorem, right?
Yeah, there's a theorem here. So let me remind you of this would be a neat little theorem to, I actually mentioned this in class. I don't remember if I really fully proved it or not. But every group G with size equal to a prime squared, where P is prime, of course, is abelian. So actually, there are only 2 groups of size 9, and this is the list right here. Okay. So I'm wondering if we can prove this. Let's try. Oh, we don't quite know how to fully prove this yet.
It's kind of related to 16 though, right? In a sense. It's kind of like the backwards way.
Yeah, it's related to it a little bit, I suppose. But the fact that we need, and we're going to actually get to this probably tomorrow if I talk fast enough, is that anytime you take the center of a group that has a prime power size, it turns out that it cannot be E. So we need to come back to this. So this would not be a reasonable question for the test at this point. But you'll see using conjugacy classes, we're going to talk about conjugacy tomorrow, that the center of any P-powered group is never trivial. And so that means, what are the choices for the center? In terms of the size of the center, what would be the options that would be remaining? If it does not have size 1,
3 or 9.
in general, it would be
No, 9 is squared. Yeah,
P or P squared, right? Now, and this is kind of the case you want, because if the center is the whole group, then your group is abelian, right? So why is this not possible? So if the center of the group was size p, can you see what's going to go wrong with that? Do you know?
It does have to do with p's prime, so p is going to be odd, so the multiple 2p squared is going to be odd. And then if you have, so you have an odd, a group that has odd order,
Mm-hmm.
and then you have, the order of that group is going to be odd as well. So you can't commute to, there has to be an even number of elements that are in the center, right? I'm not sure how to word that.
It's not necessarily true.
Okay.
Yeah, the center could be odd size. It could be a group with an odd-sized center, I think. For example, I can give you a group that has a center with 3 things in it. This would be a good question. Give me an example of a group that has a center that has exactly 3 things in it.
C3.
Whoa, that sounds hard.
Z3.
Well, I was,
Give me an example of a non-abelian group that has a center with 3 things in it.
So cross, yeah.
Yeah.
T,
You just have to do something like that, right? The center of S3 is trivial. Well, we just proved a minute ago that the center of this is equal to the center of the first part crossed with the center of the second part. There's 1 thing here, there's 3 things here, so that's 3 things. Okay, well, there you go. Okay, so anyway, I'm just rambling right now. No, there's nothing wrong with having an odd-sized center, but I'm bringing this up to remind you of a very important theorem, which I did prove in class, which is, what could you tell me about this quotient group? So, how big would this quotient group be? If the center has size p, then how big is the quotient group?
P.
P as well, right? And this means that the quotient group is isomorphic to ZP. In other words, this is cyclic, right? Does anybody remember a theorem about this? If the G mod, the center, is cyclic,
G is abelian.
then G is abelian. Okay, a word to the wise. Make sure you know this theorem. This is very useful. Okay, so if G mod, the center, is cyclic, then your group G is abelian. I think it's theorem like 8.15 or something like that. And that then would actually contradict the premise that the center has size p. Because if G is abelian, then the center should actually be the whole group, which has size p squared. Okay, so this is actually not possible either, so we end up with the center being p squared. This does rely on a fact at the start, which we haven't quite covered yet, but I'm hoping to get there by tomorrow and talk about that. Okay?
This doesn't generalize for n instead of p squared.
Right, so there are non-abelian groups of size 27, for example. Yeah, so as soon as you put the power up a little bit, it's no longer quite so easy to work with that. What about groups of size 10?
Z10.
Okay, Z10, definitely Z10 because, well, you always have a cyclic group of every size. Anything else? Would there be any other abelian groups of size 10? If you factor 10, it factors as 2 times 5, right? So you don't have, using the fundamental theorem of finite abelian groups, right? You've got to write a group of size 10 using powers of primes. Well, the only way to do it would be Z2 cross Z5. But remember, Z2 cross Z5 is Z10 because 2 and 5 are relatively prime. Any number, this is actually one of your homework problems for tomorrow. Any number that is square free, meaning that the factorization of the number has no primes to a power bigger than 1. For any group of that size, you will only have one abelian group because you can't combine, like there's only one way to combine. Like if I just have a bunch of primes, and I'm just crossing them together, and these are all distinct primes.
They're always relatively prime.
They're always relatively prime, right? This is going to be isomorphic to Z, P1, P2, P3. Right? It's just automatically going to be true. So if there's no powers on any of the primes, then that's all you're going to see. Yeah.
The reason we're using all this is there's like a result that we're using for all of these under the surface, which is every finite abelian group is isomorphic to Z.
A direct product of cyclic groups of prime power order. That's this fundamental theorem of finite abelian groups. So every finite abelian group is a direct product of cyclic groups of prime power order. The only primes inside of 10 are just 2 and 5. So how can you build a group of size 10 using Z2 and Z5? Well, you cross them together, and that's really the only thing you can do. When you cross them together, you just get Z10. Now, can you think of a non-abelian group of size 10? D5, absolutely. D5 would that's just the rotations and reflections of a pentagon. That one has a trivial center in that case, but yeah, that's another example of a group. That turns out to be the only other group of size 10.
Is that a fact we're supposed to know about D5? That its center is trivial?
Well,
I should say, do you expect us to know any D other than D4?
It turns out, okay, I guess I can tell you the answer, but I don't really expect you to know this. But the center of Dn, just for those of you who are curious, it's trivial if n is odd, and it consists of the identity and the rotation of, I don't know how to say this, so it's, I guess, n over 2.
So
Halfway around, if n is even. So for example, if n is 4, then you have 2 elements in the center, which are the identity element and the 180-degree rotation. So that's always the center of this group. Not that we ever covered that, but just for your enlightenment, that is true. Yeah. Okay, can anybody think about groups of size 12? What would we have?
Z12 and all the...
Z12. Now 12 is 2 squared times 3. Actually, I think this is one of your homework problems. So how else can you break this down then?
Z2 cross Z6.
Right, I could write, so if I really want to do it the way of the fundamental theorem, I should be writing this as Z4 direct sum Z3, and then I should be writing Z2 direct sum Z2 direct sum Z3. But of course, I can call this one Z12, and I can call this one Z2 cross Z6. Because the 2 and the 3 are relatively prime, so I can put this together into Z6. I cannot combine Z2 with Z6 though. Okay, so I've got those. Can anybody think of any other groups of size 12?
D6.
Okay, it'll be D6. Can anybody think of any others?
S3. S3.
S3? S3 is up here.
Oh, sorry.
It's okay. I'm not getting very far on this question yet. It's okay. I'm going to leave it on the board a little longer. Can you think of any other groups of size 12?
S4 mod Z2.
Ooh, close to what I'm thinking of. Do you know what S4 mod Z2? First of all, you have to explain, like, how is Z2 a subgroup of? You have to be careful. Is Z2 a subgroup of S4? Not really. They don't even use the same group operation, right? But I know what you're trying to do. You're trying to take 24 and divide it by 2. Does anybody?
S3 cross Z2.
Okay, S3 cross Z2. That sounds likely. Now we're going to need to stop and think about whether some of these things are isomorphic in a minute. That's going to be a question. There's another one though that I'm looking for. I'm wondering if anybody can think of.
The U's.
Not with
Is
those.
it like S4 mod S2?
S2 is actually the same as Z2. The size of S2 is 2, the size of Z2 is 2. Those are just isomorphic cyclic groups. So I won't put that one down because I don't quite know how to view S2. Well, S2, I guess, using composition, you could view it as a subgroup in that sense of S4. But that wasn't what I had in mind. It wouldn't be. The problem is, okay, so does this make sense? And I would agree that there is a S2. So S2 would, of course, just be the identity element and the cycle 1, 2. Perfectly fine to view that as a subgroup of S4, but it's not going to be a normal subgroup of S4. As we discussed in the very first example tonight, when you conjugate this cycle by other group elements, you won't get this cycle back. You'll get some other numbers in the cycle. It will not be closed under conjugation. So I would hesitate to write this group structure here. Does anybody know a group that's half as big as S4?
That's the alternating.
That's the one. That's the one. This is from the video, and I can pretty much tell you you're going to need to know about the alternating group for the midterm. So that is absolutely correct. Now, if we look at that, okay, I'm going to forget this problem 16 for a moment because we've managed to find another very good problem to work on here. I want to think about which of these might be isomorphic and which ones are not. This is a very good question. Now, the alternating group, A4, just to remind you, that consists of the permutations in S4 that are even. So that'll include the identity element, obviously, and any other elements that can be expressed as an even number of transpositions. So if you go back to my video, anything that is like 2 transpositions would be even because it consists of an even number of transpositions. So we would have all of these elements. And then in addition to that, any cycle of odd length, if you remember from my video, like this element here, 1, 2, 3, is actually even as a permutation because this can be written as, what would it be, 1, 3, 1, 2, right? So if you, no, got it backwards. 1, 2, 1, 3, right? So there's 2 transpositions here. They're not disjoint. In this case, this is not the simplified version, but that's what it would be, and it's 2 transpositions. So the cycle 1, 2, 3 is actually even, as is 1, 2, 4, 1, 3, 4, 2, 3, 4, and then we can reverse all of these. So take the inverses of each of them, 1, 3, 2, 1, 4, 2, 1, 4, 3, and 2, 4, 3. So we were supposed to be talking about groups of size 8, and now we're talking about groups of size 12. This is the alternating group. There's should be 12 elements listed in total there in that whole list. So in terms of isomorphisms, what are we thinking? Like, obviously A4 has a ton of elements of order 3. What about any of these other groups? So for S3, for example, crossed with Z2,
S6.
you're going to have, what kind of elements could you make here? I guess I can get rid of this theorem now. We've had this up here for a while. Give myself some room to write things down. So just looking at orders of elements is what I'm kind of thinking about here. Also, I should mention that the center of this alternating group is going to be trivial, again, just in the same way as it is for the symmetric group. So we can maybe take advantage of that too. But, so that's A4. What about, let me just write down S3 cross Z2. This is going to have 12 elements in it. Let's just write them down. We're going to have E and 0, 1, 2, and 0, 1, 3, and 0, 2, 3, and 0, 1, 2, 3, and 0, and 1, 3, 2, and 0. And then all of that again, I'm missing some parentheses here. And all of that again with a 1, right? So E and 1, 1, 2 with 1, 1, 3 with 1, 2, 3 with 1, 1, 2, 3 with 1, and 1, 2, 3 with, 1, 3, 2 with 1. So let's just take, since we've got these two groups on the board so far, are they isomorphic? This is like a great question. I could easily do this on the midterm. Give you two groups and ask you, are they isomorphic?
No.
Doesn't one of those elements has order 6?
Right, right. That's one way to think about it. Can you tell me which of these elements has order 6?
The last two.
These guys, right? Yeah, because you have a cycle of length 3, and then you have the number 1, which has order 2. The LCM of 3 and 2 is 6, so that's not the order of any element over there, right? Or you can use the center and say the center here is trivial, but the center here has actually has both of those two elements in it, right? The center would be just E cross Z2. Okay, so far what we know is that these, the second and third one are not isomorphic, right? So we have two different groups of size 12. Now let's throw D6 into the mix. Now D6 is going to be a little bit interesting. Let's think about it. Does everybody understand what D6 is? Hi. You want to grab a chair? Or? It's up to you. We're just playing with groups of size 12. We're trying to classify all of them.
The sextagon, all of the rotation.
Okay, we have all the rotations. So there'll be 6 rotations, right? You can either take the identity rotation, or you can rotate a hexagon 1/6, or 2/6, 3/6, 4/6, or 5/6, right? So I'll just write that as E, R squared, R cubed, R to the 4th, R to the 5th. We kind of have like, that's like a cyclic subgroup of D6, right? Like half of D6. Okay, and then there's going to be like, how many different reflections?
Like 6.
6 of them, right? I don't have any idea what to call them. Huh? Actually, in typical group theoretic notation, sometimes they use an S for a reflection, and then the other reflections actually just consist of taking that one reflection and multiplying it by, I didn't show this to you at all, but it would typically be written like this, S multiplied by powers of the R, and that turns out to give you reflections as well. Actually, every single one of these things down here on the second line has order 2.
Oh, because you're just,
You believe me? Let's just see. So if I square one of those things, so this is S R to the J times S R to the J. And what you can do is actually use a little property. There's a relationship between this reflection and rotation, which is that if you take S times R, it's the same as R inverse times S. It's a non-commutative group. And so if you rotate one direction and then do a flip, it'll be the same as if you do the exact same flip first and then rotate the opposite direction. Not believing me, are you?
That makes sense.
no,
It actually, you know, if you don't like that, all you have to do, we can go back to just D4 for a minute. Let's say we use this flip as our S. So imagine that I first do S. So that's going to put the 2 and the 3 here and the 1 and the 4 over there. And then let's say I rotate clockwise by 90 degrees, and that's how the square ends up. So this would be the element SR. So actually, as a combination, we did S first and then R. Okay, but what if I started with the same original square, 1, 2, 3, 4, and I first did the rotation, but I'm going to do a counterclockwise rotation. So that means I'm going to put the 1 here, the 4 goes here, the 3 goes here, the 2 goes here. And now I follow that with the flip S. I end up switching the 3 and the 4 with the 2 and the 1, and look at the numbers on the corners of the square. They came out the same. This is the element that would be R inverse first and then S. So actually, this is equivalent to what I put here. So I'll just put that there. RS is the same as SR inverse in the dihedral group. Okay, so just as a little fun fact. And so if you use that here, if you take, if I just take, so I can also do this for powers of R. So this S R to the J can be replaced by R to the negative JS. And the two S's cancel because you rotate twice, you get the identity, and then the powers of R cancel as well. The exponents add up to 0, so you get E out of that. So you have a whole lot of elements of order 2 here. Actually, how many do you have? You have all 6 of these and 1 more, right? So D6 has 7 elements of order 2. How many elements of order 2 do we have? Well, over here we only have 3, right? What about in this group? Elements of order 2. Well, any of these, well, sorry, not the first one, sorry. Any of these 3 would certainly have order 2. What else? Actually, any of these would have order 2, right? How many is that?
7.
It's 7 again. Yeah, so at least with respect to elements of order 2, D6 seems to be matching up with S3 cross Z2. How big is the center of D6? 2 things. How big is the center of S3 cross Z2? 2 things. Those match up. They're both non-abelian groups.
The order 6 matches up too, because
there's 2 elements here that have order 6, right? Exactly. So you've got R and R to the 5th. Those both have order 6 in this D6 group, and these 2 elements have order 6 right here. I'm starting to see an isomorphism coming, right? Like I could actually match these up, and it is actually true that these 2 groups here are actually isomorphically the same. Yeah?
So if in the exam you gave us 2 groups that are isomorphic, we would just go about it this way, even though this isn't really.
This isn't rigorous. Like
Yeah.
this is not convincing because how do I know I didn't just find the magic property that's going to tell these 2 groups apart, right? So this was kind of bad of me to just sort of check like 2 or 3 things and then say, oh, I guess they must be isomorphic, right? Because that's technically not enough. What you would need to do is produce an isomorphism. So I might ask you to produce one. And you kind of know what you would need to do. Like, you know that isomorphisms have to preserve orders of elements. So for example, let's say I wanted to go from D6 to S3 cross Z2, right? I would know already what f of r has to equal. It would have to be another element of order 6. Let's say I chose to do 1, 2, 3, comma 1. The minute I do that, the minute I tell you what f of r is, I've actually already told you what f of r squared is, what f of r cubed is, and right, all the powers of r are dictated now by this.
Because this would be homomorphism.
To make it a homomorphism, exactly. So you would be able to then line up all of the powers of r with exactly half of these elements. And then you could go back and say, okay, well now I have 6 other elements that all have order 2. I have 6 elements here that all have order 6 other elements that all have order 2. And you would then have to figure out if there was a way to define f of s to be one of those elements of order 2. The minute you did that, then the rest of these elements would all be dictated by, I mean, if I've told you what f of r is, and I've told you what f of s is, and if you believe that every element of D6 can be expressed in terms of r and s, then your whole homomorphism is completely determined, and you can just check whether it's going to work or not. So I might ask you to write it down. I don't think I would ask you to prove that it's a homomorphism. It would just be too much work. Yeah.
So this isomorphism that you've created, or this map, is not unique because you had to
It's
set
not
it
going
up.
to be unique. No, definitely not. I could have sent f of r to the other element of order 6, and then everything would have to be adjusted, but that would also work. Yeah.
So if you
Yeah.
if you want to prove these two things in isomorphisms, there's no like checklist of things that you can go down.
Nope.
No.
There has to
No,
exist an
there is
isomorphism.
no, yeah, I can't give you like an exhaustive list to say, oh, if you check all of these, 500 properties and they all agree, then the groups are isomorphic, because it's kind of an endless game.
But there is a list for you to check if they are isomorphic.
If they are not isomorphic, yeah. I am more likely to not make you guess as to whether the groups are isomorphic or not. If I want to ask a question like this, I'll probably say something like, explain why these two groups are not isomorphic, right? Or I might say, here are two groups that are isomorphic, now provide me with an isomorphism. Or it would be something that's like pretty obvious. Like I don't want people, these are hard things to figure out. Like we've spent 15 minutes on this now and don't even really have a rigorous justification. So you have to also put yourself in my place as the person writing the test, is what's going to be reasonable, right? Proving that these are isomorphic, D6 and S3 cross Z2 is really not something that I think is reasonable in the scope of the time you have to take the test and the sorts of problems that we've done up until now. So
would it be like a true or false with a hint to compare the centers?
oh, maybe. I wonder where you're getting that from. Is that from my sample test? Yeah, I think I have a problem on the sample test where I kind of have a hint about something like that. Okay, so I wanted to do this because it gave me a chance to bring in the alternating group. Make sure that you are comfortable with this alternating group. It is a normal subgroup of S, so AN is a normal subgroup of SN of index 2, right? All such subgroups are always normal, and it consists of the even permutations. Very, very important group within the symmetric group.
Index 2, always.
Always index 2. Half of the permutations in SN are even, the other half are odd. The odd ones don't form a group at all because you don't even have an identity element among the odd permutations. But the even permutations collectively form a group that is half the size of the whole symmetric group. Great.
Problem 16.
What's that?
Problem 16.
Oh yeah, I gotta do problem 16. We'll just blame Tuan for this massive
Wow.
diversion. Okay, let's go back to this problem here. I want to go back to a non-abelian group of size 8. Okay, I don't want you to just quote that we're talking about one of these two groups. Okay, imagine we don't know what our group is. And we want to show that there must be an element of order 4 inside of this group. So how might we prove that?
You can, you know every element's order must divide 8.
Okay, so there's a fact that's worth writing down for partial credit. Let's say you have no idea how to do this problem, but this is all about getting all the points that you can. So for every element of the group G, right, the order of that element, it has to be a divisor of the order of the group. Would you know how to prove that? It's Lagrange's theorem. Right, because the size of the cyclic group generated by A has to divide the size of the whole group. So the order of every element has to be 1, 2, 4, or 8. Okay.
Cannot be 8.
And it cannot be 8. So, however, the order of A is not equal to 8, since, do you want to give me a reason? Actually, somebody besides Robert want to give me a reason why would there not be an element of order 8 here?
It needs to be non-abelian.
Right. If there was an element of order 8, your group would be cyclic. Cyclic groups are always abelian, right? If you just keep writing these things down, right, you're going to get all the partial credit you can. So since if the order of A is 8, then G would have been cyclically generated by that element, hence abelian, and that is a contradiction. Okay, so my group has no elements of order 8. We're trying to show that there's at least one element of order 4.
So, I think contradiction here.
Thinking contradiction?
It's because you only have one element of order 1.
We have the identity element of order 1.
And then
So, right, so what would be the only way that we would not have an element of order 4 at this point?
all 7 of the other ones are order 2.
Right, okay, so suppose that every, so I'm going to say by way of contradiction, that every non-identity element, which I'll just write this way, A not equal to E, has order 2. So you have a group where every non-identity element has order 2. Does that ring any bells at all? I think we did a homework problem about this. I saw a lot of people in the homework, there was a problem on the homework you just turned in yesterday that involved elements of order less than or equal to 2. And I saw a lot of people doing cases. And I said, oh, if this is order 1 and this is order 2, then there's one thing. And I'm like, you don't need to really do that. The main point here is to just simply say that when you square the element, whether it has order 1 or 2, when you square that element, it equals E. This would be for all elements of the group, including the identity element. That's really what you're saying now. Okay? So the square of everything is E. Okay. And I'd like to get a contradiction out of this.
So the inverses,
So what do we know about inverses here?
they wouldn't work out, right? Because they actually.
Every element is its own inverse.
Okay, every element is its own inverse, right? I know what you're thinking of. You cannot have a group of odd size that's like that, because in that case you would pair up an element with its inverse. Actually, you're thinking of a different exercise. You're thinking of the exercise where there was no non-identity elements of order 2, so that everybody's inverse was a different element. So if every element has order 3 or more, then you can pair them up with a distinct inverse, and then you have the identity element here, and it's a total of an odd number of elements. Yeah, but that's actually slightly different than what we're talking about here.
Well, you could just say,
Yeah.
in particular, consider with 2 elements, A,
Mhm.
B, then we could say AB squared is equal to the identity element.
I like it. So this is AB quantity squared. We know that that equals E.
So then AB is equal to E.
AB equals to E.
Now we can just do multiply by the B inverse on the right hand side for both sides, and then A inverse on the right hand side. So you get AB is equal to B inverse A inverse.
So we'll multiply the B inverse to the other side, and then the A inverse to the other side.
And then go back around the other way. And
Well, what is B inverse?
V, there we go. Okay, I was like,
And A inverse is just A, right? So actually you end up proving that the group is abelian in this case. So if every element of a group has order 2 or less, your group has to be abelian. This implies G is abelian. And actually, if it's an abelian group where every element has order 2 or less, we can actually say, by the fundamental theorem of finite abelian groups, that this group would actually, we know exactly what it would be in this case, because the only abelian group where every element has order 2 or less is this one. So it couldn't be anything else. I mean, the only other abelian groups are Z4 cross Z2 or Z8, both of which do have elements of order 4 in them. So you wouldn't be having any problem with the conclusion in that case. Okay, does that kind of make some sense?
Well, then that just means that that's a contradiction, right?
And that's a contradiction, yes, because we had said somewhere,
Non-abelian.
yeah, this is a contradiction. So, therefore, there must exist an element of order 4. I won't write that all down, but that's exactly right. Okay, fantastic. Well, let's do another problem. This is so much fun. I love group theory. Okay, this is number 17 on the sheet. This one just says, okay, somebody was asking about larger powers of a prime here. So suppose that G is a group with size p cubed. Okay, where p is prime. And if the center of the group is not trivial, which actually we will be proving, as I mentioned, any prime-powered group, we didn't discuss this yet, but it's coming very soon. Any prime-powered group always has a non-trivial center. So I'm going to throw it as an assumption for now, but if I was asking this same exact question, say 2 weeks from now, I wouldn't give you that assumption because I would just expect you to know that for this size group, the center is always non-trivial. But let's just assume it for now, and let's prove that G is not simple. You know, one of the term paper ideas is to convince me that the only way to have a non-abelian simple group of size 100 or less is if the group is of size 60. And in fact, that group is A5, as it turns out. The alternating group on 5 letters has 60 elements in it. It's half of S5. There are no other non-abelian simple groups of size less than 100. And this fact right here allows you to throw out 27, at least. So there's no simple group of size 27. Okay, so we've kind of discussed some ideas that are relevant to this already today, but let's see if you guys have a place to start.
I don't remember if the center is a normal subgroup of G.
It is always a normal subgroup of G. Okay, so note, let's just write that down here. The center is always a normal subgroup of G.
And if it's not trivial, it must have order.
So, right, so what's the size of my center here?
Greater than 1.
It's bigger than 1, so what are the choices?
It's either P squared, or
P or P squared or P cubed, right? It's got to be one of those 3. Okay.
Isn't that it? Like in any of those cases, you have a subgroup of G, so it cannot be simple.
Okay, let's take each case one at a time. You're on the right track, but I just want to make sure we don't skip something we need to say. So if the size of the center is P, so does everybody remember what a simple group is? Maybe I should have reviewed that before
the whole thing or the identity? So there are 2 subgroups possible in the group.
So normal subgroups.
Mm-hmm.
The only normal subgroups are the trivial subgroup and the whole group, right? So the center is a normal subgroup, which basically means that if it's of size P, then you have a normal subgroup of G that's not the whole group and not trivial. So this means G is not simple in this case. That's like case 1.
Mm-hmm.
Okay, the second case would be what if the center was size p squared?
Same deal.
Same deal, right? Or in this case, you could actually go back to that thing about G mod the center. In this case, the size of G mod the center would be p, which means it would be cyclic, which would mean the whole group is abelian. And then in an abelian group, it's going to be very hard to have a simple group because anything is, any subgroup is automatically normal. But anyway, you could just, yeah, you could argue it the same way. So that means that, oh, that leads us to the third case. What do we know if the center of the group is the whole group?
Then it's abelian.
Okay, then G is abelian. So I need to still argue why is it not simple. So I have an abelian group of size p cubed. Could we have a group of size 27 that had no subgroups? Could we have an abelian group of size 27 that had?
You could split it, right?
Okay, so I'll give you that as soon as my group is abelian, right? Every subgroup is normal. This sounds like it's going to be very hard for the group to be simple because every subgroup is normal. But how do I know that I couldn't have a group that didn't have any subgroups? How do I know I couldn't have a group of size 27 whose only two subgroups are E and the whole group, and it's even an abelian group? How am I going to argue that? Yeah.
You could write z sub p and then z sub p squared, right? Like cross each other.
You're getting onto the right track. As soon as I'm in the realm of abelian groups, we have a theorem that we just learned yesterday. The fundamental theorem of finite abelian groups tells me what the possibilities are. So we have, what are the possibilities? One possibility is that G would be isomorphic to what?
CP cubed.
ZP cross ZP cross ZP.
Okay, so I'm hearing everything. ZP cubed. The second case would be, how about ZP squared, direct sum with ZP, right? And the third case would be G is isomorphic to ZP, direct sum ZP, direct sum ZP. This is by, the fundamental theorem of finite abelian groups. And I'm hoping that, so we're not going to be able to use the center because the center is the whole group. That's not going to help me prove that G is not simple. I have to figure out how to create a subgroup. I need a witness that there is a subgroup of each of these cases. Can somebody give me one or tell me how to make a subgroup? We actually have 3 problems still to solve here. I have to know, how do I get a subgroup of this one, how do I get a subgroup of this one, and how do I get a subgroup of this one, other than the trivial subgroups? Am I making this too hard?
Take G to be the subgroup.
Well, I need a proper non-trivial subgroup. To convince me that G is not simple, I have to find a subgroup that's not the whole group and not the trivial subgroup. And I don't care, you don't have to start with number 1. You can start with any of these that you want.
What if you take ZP cross E?
Down here.
Mm-hmm.
Okay, so on this one, I can make a subgroup ZP, direct sum ZP, direct sum 0, right? That would be a subgroup of G that has size p squared. And this is clearly going to be, a normal subgroup of G that's, not trivial, but it's also not the whole group. So in this case, G is not simple. This is harder than you thought, isn't it? We actually have to check these cases. What about for this one?
Same thing, but just use one ZP.
exactly. We just do the same idea here. In this case, we could take our normal subgroup. We can choose either one. Maybe I'll just choose ZP squared, direct sum with 0, right? Which again will be, everything is normal, but it's not the whole group, and it's obviously not just the trivial element, right? So I have another proper, non-trivial, normal subgroup of G. So in this case, also G is not simple.
No.
What about in the first case?
You could take another element, which is I can't remember if you need it to be relatively prime to P3 and take let that be your generator.
Okay, so we've got one thing to keep in mind. I'll get to you in just a second. If you're worried about finding subgroups of a group, you really shouldn't be, because all you ever have to do to create a subgroup is grab any element you like and form a cyclic subgroup out of it. And that'll do the trick. Now you do need to be careful that you don't cyclically generate the whole group. This group is cyclic, so there is going to be a generator for it, right? I want you to just literally think of ZP cubed as the, so think of Z27, right? If you need a specific example, like the generators for Z27 would be which numbers between 0 and 26? All numbers that are
relatively prime to 27.
relatively prime to 27. So that would be 1, 2, 4, 5, 7, 8. These are the numbers you don't want to use, right? 10, 11, 13, 14. If you use any one of those numbers and create a cyclic subgroup generated by any one of those numbers, your subgroup is going to be the whole group. Okay, so pick a number that is not relatively prime to 27, such as 3. The cyclic subgroup generated by 3 will have size 9, because 3 goes into 27 9 times, right? In particular here, I can just, instead of dealing with P cubed, I would just use the cyclic subgroup generated by P. Everything is normal in G, but it won't be the whole group because you picked something that's got common factors with P cubed. And clearly this is also not equal to the identity element. So again, G is not simple. Okay, does that make sense? So it's useful to go through all 3 cases. I know it seems so trivial that as soon as you get that this group is abelian, you feel like you've already won the game. But then you got to go do this whole thing over here. Turns out the only abelian groups that are simple are the ZPs. Yeah, just the groups of prime size. Okay.
I was going to ask that earlier.
Yeah, no worries. No worries. Okay, I'm going to do another problem. Is everybody hanging in there? Okay, we're just practicing. I'm trying to think what kinds of stuff I want to go over. Let's talk about that group of units real quick here. So here is the question. This is actually off of the group work. I think you've seen this question, but I don't know if everybody's done the group work that I sort of asked you to do on your own. So let's just talk through it together. So this is not off of the reviewed questions. This is like an extra problem. And what it says is just, to what familiar group is U28 isomorphic? If you guys tell me you've all done this problem already, I don't have to do it, but I don't know if anybody's thought about this one yet. Maybe not. If you haven't thought about it, then let's do it. Let's just do it right now. I think it'd be a good one to practice. Okay. Great. What do you think maybe would be the first thing to do?
Write down what U28 is.
Yeah, maybe we should write down what U28 is. U28. So this is the group of multiplicatively invertible elements in mod 28. So we're working with multiplication here of the numbers. So we have the numbers from 0 to 27, like we normally would for Z28. But we're not going to take all of those numbers. We're only going to take those numbers that are relatively prime to 28. So let's see if we can go through and make a list. Can you guys help me with this? What elements would you start off with? 1, 3, 5,
11. 7.
7 divides into 20.
Oh. Yeah.
9. There's the next one. Okay. 11.
Is that
I'm always read them
But
all
3
the
divides
primes.
into 9, right?
13.
Is it all the primes? No, it's not, because the 7 wasn't there and 9's there.
Oh, yeah.
13. I'll give you a little hint here, guys. Once you get halfway there, it's a mirror. So the halfway to 28 would be 14. So if I subtract 1 from 14, I get 13. So I'll also get 15. Right? And then I go down 2 here, so I'll go up 2 here. Everything's like splits right down the center. And then the next one is going to be 19. The next one is going to be 23, 25, and 27. There it is. Okay, that's our group under multiplication. By the way, if you're wondering, like, why do I know that that mirror works like that all the time? It's very easy to explain that, because if you just write half of this group out, what you'll notice is that the rest of these numbers in mod 28, they are just the negatives of all of the numbers that we just wrote down, right? So you can literally, so like for example, 27 is the same as -1, 25 is the same as -3. And in fact, when I'm doing calculations, I generally like smaller numbers anyway. So you may actually prefer to think of it in the second way that I wrote it there. Okay, so what might we want to do with that now?
Count them.
Figure out how big this group is. That's a good idea. So the size of U28, how many things are there? 12. Oh, we just did groups of size 12. Okay, so let's just remember U28 is therefore isomorphic to some group of size 12. So I'm going to give you some choices here, and then we'll see what you guys think. We have Z12, or it could be Z6 direct sum with Z2, or it could be, what were the other things we came up with? We came up with D6, or we came up with A4. I think those were up to isomorphism. Those were all of the groups of size 12 when we made our list. Okay, so we want to figure out which of those 4 choices is the correct answer for this group.
It's not the last two.
It's not the last 2. Why not?
U20 is a abelian.
Exactly. This is a multiplicative group of integers, definitely abelian. These guys are non-abelian over here, so I'm going to cross those off. Okay, cross those off. And how are we going to figure out of the remaining 2 choices what is our group isomorphic to?
Order. Z12 has elements of order 12, or
Mhm.
order, yeah, and Z6 does not, has the highest order 6.
Right, maybe we want to figure out the orders of these elements. Might even be useful to just make a little table here. You know, X, and then put the order of X. I can just write down my numbers here. This might take a little bit of a patient calculation. I'm going to use the negatives because it's going to be faster, just to give you a heads up. Okay, so under multiplication, of course my identity element is the number 1, right? So what's the order of 1? 1, okay. Are any other numbers in this list easy to do?
-1.
-1 has what order? I see people taking 27 and trying to square it all day long. I'm like, no, just change it to -1. Square that instead. Okay, great. Well, let's take another one. Let's take 3. Now remember, the order of The possible orders have to be divisors of 12. So these are the possible orders that our elements could have. So 3, it obviously doesn't have order 1. Does it have order 2?
No.
No. Does it have order 3?
The order
No.
3 is negative 1.
Pardon me?
3 cubed is negative 1.
3 cubed is negative -1 in this group. So that tells me that 3 to the, whoops, that's supposed to be a 3. 3 cubed is -1, so therefore,
6.
right, if you take 3 to the 6th, you're just going to be taking 3 cubed and squaring it, which is going to be 1, right? And so, yeah, so that tells me that the order of 3 is 6. By the way, you might have noticed that I skipped over order 4 right there. So we did order 1, 2, 3, then we got kind of excited and recognized that the order is 6. Do I need to go back now and make sure that the order wasn't smaller than 6? Why not? Why couldn't the order of this element be 4?
So it wasn't 2?
Say again?
Because it wasn't 2, so. If,
Well, it could be 4 without being 2.
well,
If it was 6, then its order could possibly be 2 or 3.
Right, once you find so if x to the k is equal to e, then the order of x has to divide k. So at this point, as soon as I find the 6th power of my element is equal to e, the order has to divide 6, and 4 does not divide 6, so I don't need to check that one. Okay, so great. So I have this element here of order 6. Okay, what do you want me to check next?
-3 would also be 6, right?
Well, let's see. -3,
Actually, no, it would be 3.
if I cube this, I get -27, which is 1, right?
Oh.
Yeah, so this one is, it's a little confusing. This one's actually 3. Yeah. Okay, what about, I guess we could try 5. So the order of 5, so 5 squared is obviously not 1 in mod 28. What about 5 cubed? What I would do for that is I would write it as 5 squared times 5, and 5 squared, you see, 5 squared is actually 25, and 25 can be changed to -3. So this is -3 times 5, which is -15. Okay, so the order is not 1, 2, or 3 so far. What about order 4? This would be 25 squared, which is just -3 squared, which is 9. That's not equal to 1. What about order 6? 5 to the 6th would be 5 cubed squared. I guess we could look at it that way. Or we could look, actually, I would rather look at it as 5 squared cubed, because 5 squared is -3. When I take -3 and I cube that, I get -27, which is 1, right? Darn it. Okay, so this is order 6 as well. Okay, that's order 6 as well. So you just have to kind of keep going this way. You guys kind of have the idea? Maybe I don't have to like take too much time to keep doing this. You're going to look and see, do you ever get an element of order 12? It turns out you're not going to. So this guy has order 3. I'll just fill out the table. 11 has order 6. 13 and -13 both have order 2. 17 has order 6. And 19 has order 3. And 23 has order 6. So there's, makes sense, there's 5 elements of order 6, a few elements of order 2, a few elements of order 3. So what group does it have to be? It's the only one that's left, right? So up to isomorphism, that's going to be the answer. Okay, great. Let's do another problem. I want to do something that's, sorry, I realize I don't have, well, I do have a good, I don't have as many things about topic as I would like, so let me just find one here that's reasonable to ask you to do. You guys hanging in there okay? All right, great. Let me...
Thank you.
Sorry, I just need 1 second to think this through. Yeah, okay, I'm gonna throw a weird one at you. I'm gonna make this up though, okay? I'm gonna make this up. This should be kinda cool. Ready for an extra?
Yes.
A Dr. Ann an extra?
The doctor, that's fine.
But Dr. Annan, all group theory is cool.
That's true, but this is like really extra cool, okay? So what I'm going to look at in this example is I'm going to let C with a star on it denote all non-zero complex numbers, okay? So this is the set of complex numbers, I'll call them Z, such that Z does not equal 0, which is a group under multiplication. So, you can multiply two complex numbers, you get another complex number, certainly associative. The identity element is, of course, just the number 1, as you would expect. And the inverse of any complex number is just 1 over that complex number. Like you just take the reciprocal of it, essentially. So, just as a quick example, so if I wanted to know, let's say I took a plus bi, this is a complex number, right? The inverse of that, right? I could just write it as 1 over a plus bi, but it turns out there's also a way to express it as another complex expression, which is to write it as a minus bi over the a squared plus b squared. If you take a plus bi and you multiply it by a minus bi and you use the fact that I squared equals -1, you just get a squared plus b squared. So it cancels out to 1 when you do that. So this, you see, you can view this as just being a over a squared plus b squared. That's the real part, minus b over a squared plus b squared times I. And as long as you did not start with the 0 complex number, which would have a and b both equal to 0, this is still a perfectly legitimate complex number. Okay? Now, so here's what I want to do. Let K denote the set of non-zero complex numbers such that the modulus of that complex number, I'll tell you what that is in a second, the modulus of that complex number is 1. So this would be the set of complex non-zero complex numbers such that the modulus of the complex number is actually just the square root of a squared plus b squared. And if I square that, I want to get 1. I can actually draw a picture of this group. The picture of this group in the complex plane would just be this complex circle right here of radius 1. It's all the points on that circle. I would like to prove that that is a normal subgroup of C star. And after we do that, we're going to see if we can figure out what the quotient group would be isomorphic to. Okay?
Squaring the modulus?
I am squaring the modulus because it's equal to 1, so I just didn't want to put a square root there. Okay. If you haven't taken complex numbers or it's been a while, don't worry. Like, I probably wouldn't do this on a test because, you know, there's no prereq of math 412 or whatever here, but in a review session, I can kind of take my liberties and do some things. It's still gonna give us the idea of what kinds of questions we could ask. I mean, this would be a likely thing for me to do, would be to come up with a group that maybe you haven't seen before, and then maybe you didn't study, because I don't want people to just have everything memorized and then just pull it all out. I want people to be able to construct stuff. So this would be like a new group that we can play with that we haven't really looked at before. Did somebody have their hand up?
I was gonna ask, one of the theorems that we have way earlier is that K would be a normal subgroup if it's the kernel of a homomorphism.
Yes.
So is that something that's like...
That's a trick you could use. Yeah, I mean, you could actually try to create a homomorphism from C star to something else that had exactly K as the kernel. And that would be legitimate. Let's not do that here, but that would be a strategy that you could use. But you'd have to figure out what the map was. You'd have to figure out, what am I gonna map C star to, right? And that wouldn't be given to you, so you'd have to be kind of creative to come up with that. But you could.
I was gonna ask if that's typically something that's really difficult to do, or if that...
It can be. It doesn't have to always be that difficult. You know, so for example, if I want to prove that AN is a normal subgroup of SN, and let's just imagine for the sake of discussion that you don't know how big these groups are, so you can't use the index argument. Of course you can, because this is half as big as the whole group, but let's say you didn't know that. What you could do is you could say, well, I'm going to create a function that goes from Sn to somewhere that has the kernel being the even permutations. And maybe you have this intuition that somehow, okay, I want to make all of the even permutations go to like 0. And then what are you going to do with the rest of them? Well, maybe you just send them to 1 or something. And then you say, oh, okay, so I can create this thing, and now the kernel is going to be exactly AN, and then you have to figure out how to define this. Yeah, you could certainly do that.
You'd have to show that this is a homomorphism.
Have to show it's a homomorphism. Whatever you set up, you'd have to show it was a homomorphism. Absolutely. Okay, but anyway, let's say in this case I don't want to do that. I just want to go direct with showing that I have a subgroup, a normal subgroup of C star. Okay, so can somebody tell me what would I want to do first for showing the subgroup? Closure. Okay, closure under the operation, which in this case is multiplication. You know it says it's a group under multiplication. Even if it didn't say that, you should know that because we've thrown away 0. We're working with C star here. Okay, so let's show that this is closed under multiplication. I would recommend when you're doing these kind of things that you give me a little bit of a hint of what you're doing. So closure under multiplication, what am I going to do to start that off?
2 complex numbers.
Okay, I need to take 2 complex numbers. What do you want me to call them?
Z1, Z2.
Okay, Z1 and Z2. These are, of course, non-zero complex numbers, right?
That's B and K.
And K, I'm sorry. Typo? Yeah, inside K, definitely. Okay, so what should I do from there?
Then Z1 equals A squared plus B squared equals 1, Z2 equals D squared plus,
So there's a couple of choices I think that you have here. One is to write out the Cartesian notation of these numbers. So you could write Z1 as A plus BI and Z2 as C plus DI, right? The other thing you could do is just use a polar form of the complex numbers, but that's getting even more abstract. So let me just write like this for now. Okay, and so if I wrote the complex numbers like this, this would be where A, B, C, and D are going to be real numbers, and there's also a requirement that yeah, so these are elements of k, right? So I know that a squared plus b squared has to equal 1, and c squared plus d squared also has to equal 1. So I gotta actually write all of that out. So then I have to look at the product z1 times z2 for closure under the operation. So if I did that, z1 times z2 would be a plus bi times the quantity c plus di, and this gets a little bit of a messier product. The real part of that multiplication would actually give you ac minus bd, and the imaginary part would give you ad plus bc times I.
Yes.
Yeah, Twan?
Are we allowed to, so z1 dot z2 is an element of k if the absolute value of z1 dot z2 is equal to 1?
Yeah.
And then can you just split it up?
Yeah, that was the other way to do it. That is cleaner than this for sure, is to just use the modulus relationship. That's something that is definitely true about complex numbers. You may or may not be totally aware of that, but that's absolutely the case. So could we do it this way? Or is it going to get too messy? We would have to now check if we square this one and square this one and add them up.
Probably some factorization.
Yeah, it should be doable, right? So if we look at AC minus BD quantity squared, and then we look at AD plus BC quantity squared, we should get 1. Let's just see what we actually get. We get A squared C squared minus 2ABCD plus plus B squared D squared. That's foiling out the first term. And then when I foil out the second term, I get A squared D squared plus 2ABCD plus B squared C squared. And of course, I can cancel some stuff there. And at this point, honestly, you shouldn't even bother to try to factorize this. You should just hope and pray that it equals the thing you know you want it to equal, which is a squared plus b squared times c squared plus d squared. Can we check that? Because I do know that that will equal 1. So if that's correct, that should equal 1. Is that what I get when I expand the whole thing out?
Yeah.
Wow, it does seem to work if I just reorganize the terms like that. Great, so from that calculation, I'll just come up here, thus Z1, Z2 is in K. All right? That's closure under the operation. Okay, the next step is to check inverses. Closure under inverses. So I usually just do this one by saying something like, let Z1 be as above. Right? And then I'm going to look at the inverse of Z1 under multiplication. So it was kind of helpful that we already worked on that here. So the inverse of Z1 is A over A squared plus B squared minus B over A squared plus B squared times I. And I need to check whether that element is in K.
Denominator is 1.
So I have to square this and add the results. Is it going to work?
Yep.
Glad you guys can see it. You know, there's something, somebody told me once, is when you're standing at a board, everything is like twice as hard as when you're like sitting down. I have to actually like look at it. To square this part, I'm going to take this part, which is minus b over a squared plus b squared, and square that. And let's just see.
Well, the denominator is 1.
Oh, the denominator is 1. Da, 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 of course. So this is just a squared plus b squared, which again is just 1 again. All right, great. So Z inverse is an element of K. So we have a subgroup. Am I done? No, what else do I have to argue?
It's a normal subgroup.
That it's a normal subgroup. Okay, so K normal in C star. How do we check that?
Closure and conjugation.
You know, there's still a lot of people on the homeworks, I noticed, that they're checking normality by comparing right cosets to left cosets. It's really a tedious way to do it. It's much better, as you guys just suggested, to check closure under conjugation. Work with elements rather than cosets. Working with equality of cosets is a fuzzy thing, right? It's not very easy to draw conclusions from that. So I probably want to use closure under conjugation. Except that, does anybody have a different idea? Now that I've talked about how great closure under conjugation is there another way to do this? Got a lot of infinite groups here, don't we? By the way this group works is, you know, you're basically just basically just moving around this circle, right? When you multiply two things that are on the unit circle, it stays on. This is just the complex circle, right? So all the points are just working around that circle like that. So yeah. K is a normal subgroup of C star. Does anybody see why?
Is C star abelian?
That's it. It is abelian. We're working with complex numbers. Take Z1 times Z2 is the same as Z2 times Z1. So every subgroup is normal. Exactly. So this is true since the non-zero complex numbers is abelian. Exactly right. So we have an abelian group, so we can form any quotient that we want whatsoever, and we're always going to get a we can form any subgroup, it will always be a normal subgroup. Okay, so now my follow-up question is going to be, what do you think the quotient group is isomorphic to? And then we'll have a conjecture about it, and then we'll see if we can prove it after that. So follow-up. To what familiar group is C star modded out by K isomorphic?
My guess is either C or R.
Probably R star. Maybe.
I'm thinking,
You guys are on the right track.
because it's just going to be circles of a bunch of different radiuses, right? And
There's a good way to think about it.
since the radius is just a real number,
Uh-huh.
I'm thinking it's going to be R star.
Which is what he said as well,
Yeah.
which is almost right.
Oh, actually positive R star.
R
right?
star star.
R double star.
Yeah.
You guys are good. That's exactly right. It's just the different radii of these circles. Right, exactly. So the claim is,
Oh man.
isn't that clever? The claim is that when you mod out here, you get a group that's isomorphic to the positive real numbers under multiplication. Exactly. And I don't know whether it was because some of the homework from this recent assignment was from the section before the isomorphism theorem, but I saw lots of people trying to prove isomorphisms like this by working with cosets. And it's really tedious. You have to worry about well-definedness and just clumsy notation even, just to write down the elements of a quotient group. So what's the better way to prove, when you see something like this, what bells should go off? First isomorphism theorem, and actually if you write that on the test and you don't do anything else, like, oh, I only have 10 seconds till the exam's being collected, and you just write first isomorphism theorem there, I'll give you like 15, probably not half credit. I'll probably give you like wishful thinking. I'll probably give you some points though. Yeah.
Half credit.
I'm a generous guy, I'm just not that generous. Yeah, but I mean, just throw that stuff down on your paper. A lot of people don't write enough on their test, and then I was like, okay, I've got to be a mind reader. Man, does this person really know what they're doing? And then that's where it's harder for me to just feel good about giving out the points. So yeah, if you see something like this, the knee-jerk reaction should be to use the first isomorphism theorem. So we use the first isomorphism theorem. You knew you weren't going to get through this review session without seeing this, right? So that means I have to do what? I have to define a function from where to where?
C star to R double star.
Great, from C star over to R double star, and the goal will be to have the kernel of that be exactly this subgroup we were just talking about, which is I lost the K, didn't I? The K was the set of complex numbers, non-zero complex numbers, such that the modulus was 1. Okay, so I am ready for you.
Modulus of Z.
So fast. Yeah, you just take the complex number and you send it to the modulus of Z, which is always a positive number. So this is actually just the square root of a squared plus b squared, to be technically precise. But you know, it is kind of nice to not have to, like, this was a little messy. If we just write it in this more abstract notation and we don't use the A and the B, it'll be easier to show that it's a homomorphism. So what do we need to check here? We need to check.
Wait, is it a squared plus b squared all quantity squared, or is it just a squared plus b squared? Square root.
It's what I have written just exactly there. That's what it is by definition. Again, this is something that I probably wouldn't put on a 407 test unless I knew everybody in the room had taken a whole bunch of complex analysis. So I won't probably do that, but for the purposes of the review, it's great. So what are the things I need to check here?
Surjective and homomorphism.
F is, okay, let's say it's a homomorphism. Let's just do it one at a time. F is a homomorphism. Let me give myself some room over here. We're also going to check that it's surjective. This should be pretty easy, I think. A lot of times, if you set this up correctly, then the proof just falls right out. It's really not very hard. I have to check that F is surjective. And then I have to check that, what else do I have to check?
Kernel.
Kernel is K.
Kernel of F needs to be exactly that subgroup K that we were setting up earlier. Exactly. Okay, so let's just do these things real quickly just so I can say I did it once today. To check for a homomorphism, I have to grab two elements, right, out of C star and make sure that F respects the multiplication, right? So let's just do that. Let's let, I'll call Z1 and Z2, let's let those be elements of the non-zero complex numbers. So then F of Z1, Z2, this is how we start this off. The operation is multiplication. I just go straight to the formula, right? Which gives me the modulus of the product Z1, Z2. And this is what, Tuan, I think you were saying earlier, I can split up the modulus. This is a property of complex numbers. It's the modulus of the first one times the modulus of the second one, which is just F of the first one times F of the second one. Just like that. Okay, great. So we have that. Okay, now we need to prove that F is surjective. So let me just try to take something. Let modulus of a number be in R double star. And my job is going to be to show that that's F of something.
Consider F of Z. So Z.
I'm waiting for somebody to object to what I've done over here, because a lot of people are still struggling to prove surjectivity correctly. You see, this is not good. I don't want to go too far before I pull myself back. I'm already writing I am being biased here, and I'm already writing my positive real number. This is all that I know that I have is a positive real number, and I'm already writing the notation to be what I want it to end up being, and that's not allowed. I should not be doing that. I should be picking a completely different letter. I'll just use an X or something. I pick any positive number that has no connection to the way the function was defined, right? The only thing you're doing is grabbing something from the codomain. Okay, now, our job is going to be to come up with an input, which has to be a non-zero complex number that would get mapped to this. Say it again?
Just f of x.
Yeah, so if you had a real number and you wanted to know the modulus of it, so now we use this formula, the modulus of a real number is actually just its absolute value. So this is very easy, but I've seen a lot of people sort of starting this surjectivity off by writing the notation of the right-hand side. There was a homework problem yesterday where I think we had a group H, which was the set of all of the squares of everything in a group G, and there was a function here, f, that just took f of x to x squared. And we were like supposed to show that this was surjective, and I saw a lot of people for surjectivity write something like this. Let a squared be an h, right? And so they're already like putting it into the form of what the output is supposed to look like. It'd be much better to write something like, you know, let a be an element of h, then a is equal to x squared for some x in G, right? So you then rewrite it using what h is, and then you have your pre-image. Okay, so just be a little careful about showing surjectivity too quickly. The kernel of f equaling k, this is a set and this is a set. We have an equal sign between them. So technically you would, traditional way to do it, show that this is a subset of that, show that's a subset of that. We might be able to circumvent that, right? So I could just kind of do a series of biconditionals here to make it a little quicker. So z is an element of the kernel of f, if and only if, and we can just kind of go like this, right? This would just mean that if we take f of z, we're supposed to get the identity element of r double star, which is of course just the number 1. And that just means that the modulus of z is supposed to equal 1. And as you can see, that just means that z is in k. So this is kind of the fast way to do it. Okay, and what I would do at this point is I would have one more sentence at the end of my proof where I just say, by the first isomorphism theorem,
C star mod k.
Yep, C star mod k, thank you, is isomorphic to R double star.
So at the beginning of this biconditional, you don't have to say that z is in C star, that's already implied.
Yeah, because if you write z as an element of the kernel of f, then that means it's definitely living in here. You probably also noticed on the homework, I really try to catch every little thing I can to be very thorough in my writing there. I am not that kind of a stickler with midterms. Like, I will let you be a little less perfect in your writing because I know there's a bit of a time crunch on it. But yeah, that's definitely a good point. I'm wondering about something. So this is a surjective homomorphism. In C star, for example, we have an element I, whose order is what?
4.
It's 4, right? So what happens to that over here? The order of the image element.
It goes 2.
It gets mapped to 1.
So this gets mapped actually to 1, right? So
it
it,
sounds positive.
right? So the modulus of I is just 1. So the order of the result is now 1. So the order, a homomorphism does not preserve orders. I just want to remind you of that. So I can take an element of order 4 and it can become order 1. It's only when you have an isomorphism that orders are preserved. So what would be, so in this context here, like, actually, every non-identity element of this group has infinite order. Now this is a group of cosets. If I take any coset, what would the coset look like? It would be this kind of this is what cosets look like, right? By the way, I've also seen that. I've seen people writing cosets like this, this kind of thing, right? You don't want to do that, right? This is going to be a very confusing notation for a coset, to just call it little x or something. So try not to do that. Actually write it out as a coset. So do you agree that any non-identity coset would have infinite order? Under multiplication. So is it possible, oh maybe this is something worth reviewing. If I take a coset and I want to know what is its order, the smallest power of that element that gets you back to your identity element, right? This just means that kz to the n has to equal k, which just means, okay, this is an important thing to remember right here. Two cosets, well, a coset is equal to the trivial coset if and only if the representative lives in the coset to begin with. You guys actually proved this in the homework, okay? So this just means that z to the n is somewhere on my unit circle k, which just means that its modulus is 1. And that just means that the nth power of its modulus is 1. And because the modulus already has to be a positive number anyway, then the nth root of that gives me the modulus being 1, which just means that z is already in the subgroup K, which just means that kz is already equal to k. In other words, this is, if I have an element of finite order n, let's suppose that this coset has order n. What are you figuring out about it? It's actually the identity element, right? There are no non-identity elements of finite order in this group. If I take any non-identity element, so in other words, if this is not true, then this will not be true, therefore this will not be true, therefore this will not be true, 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 and this will not be true, no matter what n is, right? So I can also just reverse the logic that way. So every non-identity element in this world of cosets actually has infinite order. But you see, I already knew that, didn't I? Because I have this isomorphism. And if I think about, this is what group theorists do. They have a group that's kind of a pain to work with. These cosets in the complex plane, who wants to deal with that, right? That's fine. Convert it in via this isomorphism to a much more familiar and easy to deal with group, which is just the positive real numbers. Okay, the multiplicative order of a positive real number. How many powers of x do I have to take to get back to 1? Well, if I don't start with 1, if I start with a number that's bigger than 1 and I take powers of it, it just gets bigger and bigger and bigger. If I take a number that's like a fraction between 0 and 1 and I take powers of that, it just goes down towards 0, right? You never actually hit 1 unless you started with 1. So there are no non-identity elements in this group of finite order either. Totally makes sense because they're isomorphic. And I, for one, prefer thinking of this group as compared to this group. Okay, so this is the power of like, I mean, the first isomorphism theorem is allowing us to like make this really rich connection here. So, okay, I'm gonna try to kind of wrap this up. We've been going for quite a while. I just want to double check that I've done everything. Is everybody good with the cycle notation for the symmetric group and how the alternating group works, all that good stuff? Oh, I have a quick question. Sorry. I get excited. This is just fast, but I have not asked you this before, and this would make a great test question. So is GL of NR simple?
That's the matrices, right?
Yeah, these are the n by n invertible matrices under multiplication.
I thought we said that the special linear group was a normal subgroup.
Okay, perfect. So I just wanted to make sure. You guys actually proved this one, right? That this is a normal subgroup, and therefore this is a no. Okay, so that was that.
Nice try.
I tried.
Okay.
I'm gonna try one more. Sorry.
Trick questions.
Yeah. Oh, there's just so many good questions. Okay, I'm gonna try one more. And you guys, if you guys don't want me to do this one, because I know we've done this kind of thing before. Let's suppose I take a group like this. So I'll take Z15 cross Z20. And I'm gonna let n equal the cyclic subgroup generated by 12 and 8. Okay, and my question is going to be to write down 4 different cosets. I don't have to actually specify left cosets or right cosets because the group is abelian, so left cosets and right cosets are the same. This is definitely a normal subgroup. Would you know how to do this? How would you do this?
Draw your egg.
Draw my egg. Okay, I'll draw a big egg here. So this is my group G, right?
The bottom ones are going to be the cyclic group, so that's going to be in itself.
N itself. So what is in N? Like, how do you figure out what's in N?
Just add that to itself until you come back to it.
Okay, good. So I'm going to put 0, 0 in there already because I know that's going to be there. Then I have something like 12, 8. And then I'm going to 24 and 16, but that reduces to 9 and 16. Do we know what the order of this is going to be? So let's see. Again, we work in slots here. The order in the first slot is 15 divided by the GCD of 12 with 15. That's 5. So every 5 times, the first slot goes back to 0.
The GCD between.
And this one is
5 as well, right?
No, 4.
20 divided by the GCD. What's the GCD of 20 with 8?
4.
It's 4. So this is also 5.
25.
Agreed?
Yeah.
So I have to have a total of 5 elements in each coset. Okay, so I take 9, 16, I add 12, 8 to it. Again, I get, well, 6 and 4, I believe. Okay, I add 12 and 8 to that. I'm going to get...
No, it's 9 and 12, right? Or sorry, 6 and 12. Right?
Oh, maybe so.
No, 9 and 16, you add 12 and 8, you get 21 and 24.
And 14, so 6 and 14. So it should have been 6 and 14?
No,
No.
6. It should be 6 and
6 and 4, right?
Oh, it's 4. Okay, it's 6 and 4.
Yeah, 6 and 4. 6 and 4. Okay, great. And then if I go again, I add 12 more again, I get 18, which is 3. And I add 8 here, I get 12. Okay, so there's one coset. By the way, you should use that as one of your cosets. You did all that work, you may as well use it. Okay, now how am I going to get another coset? Maybe we won't do 4 cosets. Let's just talk about how would you create other cosets.
Pick something not an N, but in G.
Pick something else. What would be a good element that's easy to start from?
1,
1, 1.
or 0.
You start with 1, 1. And all you're going to do now is add these 5 things to that thing, right? So 12, 8, when you add 1, 1 to it, you get 13, 9. 6, 4 becomes 7, 5. 3, 12 becomes 4, 13. and 9/16 becomes 10/17, right? How big is this group going to be, by the way? I'm sorry, I want the size of G mod n. I'm going to form the
60.
quotient group. Is it 60? It's like 15 times 20, but then you're going to divide by 5.
Yeah, so 60.
So it's a group of size 60, and it's abelian.
You just do, so add 0, 1, and then 1, 0.
Actually, what's the factorization of 60? 2 squared times 3 times 5. How many abelian groups of size 60 are there?
4? I'm sorry, 2.
2, right, so we use our theorem, right, from yesterday. So we would have like Z4, direct sum Z3, direct sum Z5, that's one choice. And then the other choice would be to change the Z4 to Z2 plus Z2. The Z3 and the Z5, I can't do anything with those because those are just the first power. Those are your two possible groups that this could be. To figure out which one is correct, you would try to figure out whether you have an element of order 60 or not. Actually, I think that's pretty easy.
1, 1.
Yeah, what's the order of 1, 1? How many times do you have to add 1, 1 to itself to land down here? Well, I don't see anything here of the form, x comma x. So you're going to go more than 15 times already. So the order of that coset, which by the way would be written this way, has to divide 60. But it's pretty obvious that it's more than 15. Because you don't see 2, 2, 3, 3, 4, 4, or 5, 5, or anything like that. When we finally get to 15, 15, that would be 0, 15, which isn't here. So the order of this element is more than 15, but it has to divide 60, so you're really running out of choices now. It could be 20 or 30 or 60. So try 20. Is the element 20, 20 down here? Well, don't forget, you have to reduce 20, 20 in this group. And when you reduce 20, 20, it would be 5, 0, right? Which isn't here. So this element does not have order 20. What about order 30? But I have order 30, I would have to see the element 30, 30 down here. Well, 30, 30, when reduced, would look like 0, 10. And I don't see 0, 10 down here, so this element doesn't have order 30. So this is actually a group of size 60, which means it's actually this group right here. Wouldn't that be a good question? I like it. So something like that is kind of a relatively fun little calculation. I could ask a couple things, write down a couple cosets, think about how big the group is.
It would be that one because that one's isomorphic to Z60.
And this is, so this is isomorphic to Z60 because 3, 4, and 5 are relatively prime. That's kind of where that's coming from. Okay, I just saw that on my sheet here. I thought I should at least mention that. These are just coming from old quizzes when I used to give quizzes for this class. If you're looking for things to practice, grab a study buddy and throw questions at each other, oh, what group is U50 isomorphic to? Just make up your favorite number and see what you can do. Write down all abelian groups of size, 360, and tell me which of them have elements of order 180 in them, or something like that. So you can make up questions left and right, pick your favorite numbers and play with them. I would definitely be reviewing the applications of Lagrange's theorem and the uses of the first isomorphism theorem. Don't get overwhelmed with this book. There's a lot of stuff in here that I wanted to give you guys the highlights, so I didn't really do it all in full detail. I think we've been pretty comprehensive. But
Can you just quickly remind me what SL is?
oh, these are just the matrices of determinant 1. Yeah. So that's always normal inside of GL. Actually, so using properties of determinants, you can show that. So, does anybody have any other questions for me, or are we all just fried for the night? You know, when I was a grad student, I would do these review sessions that would go for like 7 hours. I was like a TA, and of course I had a lot more energy. And we would start doing problems, and nobody would leave. Like, I would be there for like 4 or 5 hours, and nobody's leaving. I was like, why are you guys still here? Like, oh, because the minute we leave, you're going to do some problem that is going to be exactly what's going to be on the test. And I wasn't writing the tests back then. It was the professor who wrote the tests. So I was the good guy. I was trying to help everybody with their studying and everything. I was just coming up with problems, and we just go for hours. We actually took dinner breaks and came back. And yeah, well, I thought we were going to start seeing sleeping bags showing up and people camping out. I finally had to put an end to it and say, all right, I think I'm done. But I now sort of do that a little bit sooner than I used to. So I think we've done pretty good. I didn't go over everything in this review session packet, so you could look at the problems and maybe there'll be some that, I mean, I tried to get the spirit of a lot of them, but you might want to take another look at it, make sure that, you know, if there's anything there that's bothering you, definitely let me know.
You're gonna record tomorrow too, and like post it up.
I'm not gonna probably post both of them up. I'm gonna see how this turned out.
Okay.
And I might post up this one. Otherwise, I'll if it didn't turn out, I'll try again tomorrow.
Okay.
It should be a similar review though. Yeah. Was it helpful?
Yes.
At all? Yeah, just kind of
Thank you.
give you an idea of what to look at. Okay, well, I'm gonna call it a night. I think we all are.
Yeah.
And I will see you guys again soon.